Howdy folks, in this video we are going to discuss the singular value decomposition, sometimes better known by its abbreviation, the SVD. As always, you can find all of the code used in this video along with additional written notes and a list of references at the top GitHub link in the description of this video. If you have any questions, comments, or concerns throughout your viewing of this discussion, do not hesitate to let me know. But without further ado, let's discuss the singular value decomposition. So this is the singular value decomposition for some m by n dimension A matrix. This matrix decomposition will apply to square and non-square matrices, and it's a decomposition into these three matrices, right, as you can see right here, both U, sigma, and V transpose. But before we dive deeper into this matrix decomposition, let me just briefly say that the singular value decomposition is a very popular topic in linear algebra and is very well covered here on the internet, particularly with some great videos by great content creators, including Dr. Gilbert Strang over at MIT OpenCourseWare, and so I'll encourage you to check out other content on the SVD to gain a better understanding of it. This clip also from the Lex Friedman podcast is also fantastic. Okay, so back to this singular value decomposition. Again, we can decompose a square or non-square m by n A matrix into these three matrices, U, sigma, and V transpose. So what exactly are these three matrices? Well, let's first discuss the U matrix and the V transpose matrix. If we define the variable r to be the rank of our A matrix, our U matrix will have the dimensions of m by r, so it's not necessarily going to be a square matrix. And the same thing goes for our V matrix, which will have dimensions n by r, so then V transpose will be r by n. Both the U and V transpose matrices are what we would consider to be orthogonal or orthonormal, more specifically, matrices whose columns are orthogonal and normalized, so that when we compute U by U transpose or U transpose by U, or V by V transpose, or V transpose by V, we get back the identity matrix, implying to us that U transpose is U inverse and V transpose is V inverse. A very, very useful piece of knowledge for us to have. Now, if we take a look at the one matrix I left out, this sigma matrix in the middle, this is the matrix that makes this matrix decomposition so particularly interesting and powerful. This sigma matrix, again, if we define the variable r to be the rank of our A matrix, will have the dimensions r by r, making this whole matrix multiplication work out so that when we recompute our A matrix, we do get back the m by n dimensions of the matrix. This sigma matrix in the middle is going to be a square diagonal matrix with what are called the singular values along the diagonal of that matrix. These singular values are going to be ordered from greatest to least along the diagonal. So the greatest value will be in that top diagonal place. The smallest singular value will be in the last place along the diagonal. And all of these values are going to be strictly positive. And so, why are these singular values of any particular interest? Well, because if we have a square matrix, an m by m matrix, we can compute eigenvalues for that matrix. But if we have a non-square matrix, computing eigenvalues is particularly tricky. The next best thing that we can compute that's analogous in a way to our eigenvalues are our singular values, which of course we get in this sigma matrix of our singular value decomposition. And so that's where we will start. We will start by figuring out how we can compute these singular values. Now, the way that we're going to do this actually is quite simple. We will either compute A transpose A, which will result in an n by n dimension matrix, or we will compute A by A transpose, which will result in an m by m square matrix. Both of these are going to nevertheless result in a square matrix, and so we can compute the eigenvalues for that matrix product. to get the singular values, we will just take the eigenvalues we compute and take the square root of them. The square root of the eigenvalues of A transpose A or A by A transpose will just be a singular value. Then we're just going to sort them from greatest to least because they're going to have to be positive, and that's how we compute these singular values. To construct the sigma matrix, it's just a matter of sliding those singular values into the correct spaces along the diagonal of a diagonal matrix. But now the real question is, when do we know when to use A transpose A or A by A transpose? Does it matter whether we pick A transpose A or A by A transpose? Well, the answer is yes, it does matter. If M is greater than or equal to N, we want to use A transpose A, which will result in a N by N square matrix. N, of course, being less than or equal to M, will result in a smaller square matrix for us to work with. That's beneficial to us. If M is less than or equal to N, then we will use A by A transpose, which will result in an M by M dimension square matrix. Again, with M being less than N, it will result in a smaller square matrix. We want to work with as small of a square matrix as possible. Now, to see how this all works and to show that just computing A by A transpose or A transpose A works in helping us compute the eigenvalues, and then the eigenvalues are just the singular values. We can slide them into this square matrix. Let's take a look at some computer code. Here you can see in this quick block from the notebook, which again is at the top, GitHub link in the description of this video, you can see that we are generating first a random 10 by 4 non-square matrix with integer values between -100 and 100. Then we are going to compute A transpose A, and we are going to compute the eigenvalues and eigenvectors of A transpose A using the NumPy lineage eig function. Recall that we're using A transpose A here because our matrix is 10 by 4 in dimension. Then we're just going to take the square root of all of the eigenvalues, and yes, I realize I forgot to put in a sort function because this isn't necessarily going to give us the singular values in order from greatest to least, so you're going to have to sort them. That's my fault. And then we're going to also confirm that these singular values are what we expect them to be by using the NumPy lineage SVD function and passing in that same A matrix. Moving to the terminal output, you can clearly see here that our A matrix is, in fact, 10 rows by 4 columns in dimension. A transpose A is 4 by 4, so that is the better of the two square matrices that we want to compute. Also note that with A transpose A, it is not just a square matrix, but it is a symmetric matrix where we have values, equivalent values in opposite positions. In any event, though, the singular values that we get from direct computation of A transpose A by computing the eigenvalues and then taking the square root of them are 245 and some change, 204 and some change, 125 and some change, and 81 and some change. And for those who are not familiar with the and some change terminology that I'm using here, I just mean the decimal points after. When we compute the singular values from the NumPy lineage SVD function, we get effectively the same exact thing. So now what about our U and V transpose matrices? How are we going to compute those? And it's not to say that these matrices are any less important than the sigma matrix, but in many cases, or applications at least, of when people are going to compute an SVD, they're mostly just going after the singular values, and they don't usually care too much about U and V transpose. But to better understand this matrix decomposition, we need to understand how we can compute these in the relationship between sigma, U, and V transpose. But to better understand this, we're going to need to take a quick detour and review some of our understanding about eigenvalues and eigenvectors. If we have some square A matrix, and we are working with it in a type of linear system, our A matrix multiplied by an eigenvector is going to be equivalent to an eigenvalue times that eigenvector, really the eigenpair. For a square A matrix, we will have multiple eigenvalues and eigenvectors that we can group into matrices. So this lambda matrix right here on the far right is going to be a square diagonal matrix similar to our sigma matrix, except it contains our eigenvalues. Our eigenvectors are grouped to be the columns of our Q matrix in this case, so we're not really changing anything. Thus, for us to represent our A matrix properly, we can compute this right here, which is better known as the eigendecomposition, where we have our Q matrix containing the eigenvectors of an A matrix, and the lambda matrix being, again, a square diagonal matrix that has our eigenvalues along that diagonal. Now, if we come back to our A matrix right here that is non-square, where we can compute a singular value decomposition for this matrix, to get an understanding of our U and V transpose matrices and how we might get them, we're going to take a look at what happens when we compute A transpose A, for example. When we compute A transpose A, we will get V sigma transpose U transpose by U sigma V transpose. Notice that we get a U transpose U right in the middle here, and our U matrix and V matrices are orthonormal matrices, meaning that it gives us back the identity matrix, so we will simplify this all down to being V sigma squared V transpose, because the transpose of a diagonal matrix is just itself. And so if we stack this up to a square matrix that we get for A by A transpose, we know that it will have an eigendecomposition because we can compute the eigenvalues for it. And if we look very closely at each one of these, notice that Q and Q inverse, we have Q and Q inverse, and we have V and V transpose that stack up to one another. V transpose is just V inverse, so those are very close to one another. And so what this gives us is our relationship between our eigenvalues and our singular values, telling us that the singular values are just going to be the square root of the eigenvalues based off of this relationship. So, because we have a square matrix where we can have this eigendecomposition here, where we know the eigenvalues are in that lambda matrix, and the columns of our Q matrix are just our eigenvectors, well, we can use this little bit of knowledge that we have here from our derivation of the eigendecomposition to look at what happens with a square A transpose A and the SVD, getting back that V sigma V transpose, to show that our V matrix, in this case, is just going, the columns of that V matrix are just going to be those same eigenvectors. And so when we compute the eigenvalues using the NumPy lineage eigenfunction and the eigenvectors, we get everything we need to compute two of the matrices that we need in this singular value matrix decomposition. But how do we get our U matrix? Well, we get our U matrix by just computing, kind of doing the inverse in this case, and computing the columns of our U matrix. Or, more simply put, because we're going to do this on the computer, we get that U is just A by V by sigma inverse. And a sigma inverse is pretty simple and straightforward for us to get because it's a diagonal matrix. So it's as simple as just inverting all of the values individually along the diagonal of the matrix, or basically inverting all of our singular values. Okay, so over here in the code, you can see that we're going to test this all out now, and so first things first, you can see that we are taking the transpose of our eigenvectors, because it's going to be V transpose after all, and we're going to compare that to what we get for V transpose from the NumPy lineage SVD function. Moving down to the terminal window, or the terminal output, you can see that all of the values here are pretty much exactly the same, except for a couple of minus signs. That just boils down to the numerical methods that are being used on the back end. Moving on, we can compute our U matrix right here by computing A by V by sigma inverse, and we are going to compare that to what we get from the NumPy lineage SVD function for our U matrix. Again, if we take a look at the terminal output, you can see here that with the exception of a couple of minus signs, again, because of the methods being used, you can see that we get the same exact thing. Just to double check that even once further though, in these last two lines, we are taking a look and trying to recompute our A matrix using our raw computed U, sigma, and V transpose matrices. And as you can see with our terminal window, we get a nice clean matrix right back, which is exactly equivalent to our A matrix from the beginning. But what happens for A by A transpose? Obviously, we want to use A by A transpose when M is less than or equal to N. But what happens if we try that for when M is greater than or equal to N? And so we can try that out right here in this code block where we're going to compute A by A transpose. Then we're going to compute the eigenvalues and the eigenvectors, take the square root of that to see what the singular values are that we end up getting. Notice right away that this results in one pretty noticeable problem, that A by A transpose, and yes, I do realize I forgot to change the label here. If I were to ask you, do you want to work with a 4 by 4 matrix or a 10 by 10 matrix, you would almost certainly choose to work with a 4 by 4 because it's going to be a heck of a lot smaller and it's going to be a lot simpler to work with. To complicate things even further, look at our singular values that we get from A by A transpose when M is greater than N for our dimensions. Notice that we get back some of the same singular values, but we also get additional singular values. We get 10 singular values, some of which are complex numbers. That very simply is not going to work out nicely because our sigma matrix, as we said from before, is R by R in dimension. So we're going to have to figure out which one of those singular values we need to throw out. Do we just take the first 4? Do we need to take all of them? Do we only take the real ones? That's why we only use A by A transpose when M is less than or equal to N. A similar issue will happen if we decide to use A transpose A when M is less than or equal to N. It just isn't going to work out nicely for us. So let's say now that we want to compute our U and V transpose matrices for the case of M being less than or equal to N. Well, of course, we're going to use A by A transpose in that case. And so we're going to do the same thing right here because things change up a little bit differently. Notice that, again, A is U sigma V transpose based off of our decomposition. And then A transpose gives us V sigma U transpose. Well, notice that in the middle here we have V transpose V this time. So this simplifies down to U sigma squared U transpose. Again, stacking that up to our eigen decomposition of a similar or the same A by A transpose matrix, we can see that the same relationship still holds between lambda and sigma squared. So we're going to compute the singular values in the same way, and this time the eigenvectors are going to be the columns of our U matrix, not our V matrix. And if we take a look at this eigen decomposition again, we will notice that the columns of our U matrix are just going to be our eigenvectors this time. So how do we compute this V transpose matrix? Well, we just do what we did before, and this time V transpose is just going to be sigma inverse U inverse, and that's easy for us to compute because sigma inverse, inverse of a diagonal matrix, is very simple and straightforward for us to get. We just invert each individual value along the diagonal, and U inverse is just U transpose. In this block, you can see that we are generating this time a 4 by 10 B matrix with integer values between -100 and 100. This is definitely a n greater than m case, so we're going to use A by A transpose, or in this case B by B transpose. We'll compute B by B transpose. We are going to compute the eigenvalues and eigenvectors using the numpy lineage eig function. We'll compute the singular values by taking the square root of our eigenvalues. Again, yes, I realize I forgot to sort them. And we will compute a SVD using the numpy lineage SVD function to check our results. Let's take a look at those singular values. Here you can see, here's our singular values for A by A transpose. Again, I apologize, I forgot to change the wording with this, but then we also get the diagonal from the sigma matrix for the same decomposition, and we get the same exact singular values, so that works out perfectly for us. In this next block, we are going to take a look at our U matrix, which is just going to be the eigenvectors of B by B transpose, and then we're going to compare that to our U matrix that we got from the NumPy linalg SVD function. Going to the terminal output right here, you can see that these are, again, the same, except for a few minus signs. And again, as I've stated before, that just boils down to the methods that are being used on the back end related to computing the eigenvalues. Which, by the way, I can't even realize I forgot to mention until now. I've done a whole video on some of the different methods for computing eigenvalues. You can check that video out. Linked in the description if you haven't seen it and you want to see it. And you can even check out some of the videos I've done on the QR decomposition, because you'll better understand why the methods for computing singular values and eigenvalues differ significantly based off of some of the methods that are used for computing a QR matrix decomposition. Anyways, we move on down here to V transpose, and we're using that same formula that we ended up seeing from before. This formula right here of V transpose being equal to sigma inverse U inverse A. In the case of our code, that A matrix is just going to be our B matrix, of course. And so you can see right here, here is our sigma inverse. Here is our U inverse, which is really just U transpose, and then we have B. And going to the terminal output, again, you can see right here that our V transpose matrix and our V matrix, in this case, are actually equivalent with one another. And so, folks, pretty simply put, that is the singular value matrix decomposition. It is a very, very powerful matrix decomposition that can apply to both square and non-square matrices. And the fact that it applies to non-square matrices really gives it a heck of a lot of its power, because you can't compute eigenvalues for non-square matrices. So a lot of people revert to using singular values. Not to mention there is tons of applications for the singular value matrix decomposition. But just to remind everybody, here's the dimensions of our SVD, the U, sigma, and V transpose matrices. And the real power and the main interest that many have with this singular value decomposition comes from these singular values in this sigma matrix in the middle. And you can almost certainly guarantee that we are going to cover some of the different applications of the SVD and these singular values. So I want to thank you all very much for watching. If you have any questions, comments, or concerns, again, don't hesitate to let me know. But again, thank you very much for watching, and I'll hope to see you all again next time.